Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. The origins of this playlist are in a conversation that I had with my PhD supervisor many years ago. Once he asked me, do you know about the fundamental group? And I responded, yes. And to which he responded, oh, that's good. That means that you also know about Galois theory. Now, up until that time, I thought these subjects of the fundamental group in topology and Galois theory were completely different things, and his answer suggested that actually they were part and parcel of the same theory. And that is indeed the case, and it took me several years to understand why this is so. So what I want to do in this playlist is give a course in Galois theory which is unlike any other course as it is taught. And what it is designed to do is basically to tell you about the ideas and principles in Galois theory and how it is used in research, rather than simply as a means to show that you can't solve the quintic equation via radicals. So at heart, Galois theory is about using symmetry. It's an application of group theory to study things like fields and topological spaces. And in this video, I just want to show you some examples of Galois theory as it is used in things that you already know about, okay? So there's some hidden Galois theory in things that you already know, okay? And the first example involves real polynomials, and I want to raise a very simple question here that you can ask. What are all the monic irreducible polynomials over R? Now, hopefully this is an example that you would have seen before and you know the answer to, but I want to frame it in terms of using symmetry and the ideas of Galois theory. Okay, so the first thing to note is that if we were to change this question and not look over the reals but over the complexes, it's a very easy answer, and that's because of the fundamental theorem of algebra. Okay, what are all the monic irreducible polynomials? They have to be linear, and so they're going to be of the form x minus alpha. So if the polynomial is over x minus alpha, well, alpha is any complex number. Okay. And so that's the answer over the complexes. So let's now move to the reals. And the basic idea in a lot of uses of Galois theory is that if you want to understand something, for example, over the reals, okay, you understand it over a simpler context like the complexes, and try to extract the answer from there. And the way you do that is you introduce a group, okay? And that's called the Galois group. So in this case, the Galois group, I'll denote G here, and the usual notation for it is GAL for Galois group. And that's of C over R. It's quite easy to say what this is. Okay, what you can do is you can look at the field automorphism from C to C, which is just conjugation. Okay, that's sigma. This has order 2, so it generates an order 2 group, and that's the Galois group of C over R. Okay, so that's the symmetry that's involved here. So in what sense is it symmetry? Okay, and how does it relate C and R? So it is a field automorphism of C. What are the things which are fixed by conjugation? Precisely the reals. Okay, so that's in what sense it's symmetry. Okay, so the real numbers are precisely the things which are symmetric under this conjugation. Okay, they're not changed when you conjugate. Okay, so let's address this problem now. So suppose we have some p of x, which is some real polynomial, okay, and it's irreducible. Okay, so how do we get a handle on all of these p of x's, these irreducible real polynomials? Okay, so the way to think about this is that, well, what you can do is that you can factorize this over the complexes first. Okay, and then the way you do that is you look at all its roots. Okay, so you pick one of its roots at alpha and c, and then what happens is that, well, what is this p of x up to a scalar? Okay, it's just the minimal polynomial over R of that root. Okay, so that implies it's the minimal polynomial of some root alpha inside the complex numbers. Okay, so now we've changed it from looking over the reals. Okay, we say that you can get a handle on all of these p of x's just by looking at all the complex numbers and looking at their minimal polynomials over R. Okay, so how do you get a minimal polynomial over R? Okay, so this is where the Galois group comes in. Okay, so what you want to do is you want to find a real polynomial such that alpha is a root of that real polynomial. So let's see how you do that. Okay, hopefully you can see it already. So alpha is the zero of what? Well, you can look at x minus alpha times x minus alpha bar. Okay, so hopefully you know already that it doesn't matter what complex number alpha you put in here. Okay, when you multiply these two linear factors, so these are the irreducible polynomials over C, when you multiply these two of them, it will actually have real coefficients, and that's quite easy to see. Okay, the constant term is alpha times alpha bar, and the coefficient of x is going to be negative alpha plus alpha bar, which is negative twice the real part of alpha. Okay, so that's also going to be real, and of course the leading coefficient here is 1. So this is actually real. Okay, so the way to think about why this works, okay, and if you want to try to do this in more general context, is the following. Okay, so what's happening here is that if you look at this, this is involution. It's a field automorphism, so it extends to a ring automorphism of C of x. Okay, so what you can do is that if you apply conjugation to each of the coefficients of a polynomial over C, okay, that defines a ring automorphism of this. And of course, the fixed point of those that automorphism, as you extend conjugation to C of x, is just those with real coefficients, where all the coefficients are fixed by conjugation, that is, are irreal. And what happens if you apply this conjugation to this polynomial here? Okay, so remember what happens here is basically what are the alpha and the alpha bar? This is an orbit of this alpha under this group. Okay, so what happens if you apply this sigma is you just swap these two factors. So of course it stays the same. Since it stays the same, of course this has to be a real polynomial. Okay, so that's the more sophisticated way of doing it, and that really shows you how symmetry is involved. Okay, so where does this expression comes from? It comes from the fact that you're looking at an orbit of this alpha under this group here. Okay, and then that tells you straight away what the monic real irreducibles are. So what you do is you just look at all the alpha inside C and look at their minimal polynomials. So let me write down their minimal polynomials. If alpha is complex but it's not real, then it can't be x minus alpha, but this is a real polynomial such that it is a root, so it has to be this product here. Of course, if alpha is already real, then x minus alpha is the corresponding minimal polynomial with leading coefficient 1. Okay, so this is an example of how you use Galois theory. Okay, it tells you. And in general, this is something that's very important. It can tell you about minimal polynomials. Okay, and in this case here, it's telling you all the irreducible real polynomials. And the answer is quite nice, and you can see you either get quadratic ones or linear ones like that. Okay, and it can tell you precisely what types of quadratics you get as well. Okay, so that's an example of how you use Galois theory in algebra. What about using Galois theory in topology? Okay. And so the question I want to have a look at here is quite simple. It's just to find interesting line bundles on the circle S1. So firstly, if you're not familiar with this idea of a line bundle, let me just tell you what it is. So basically a line bundle on any object is a line, say here a real line, R, which varies smoothly as you move along this S1. Okay, so firstly, what's an interesting line bundle as opposed to an uninteresting one? So an uninteresting one is S1 cross R. Okay, so how is this, do you think of this as a family of R's for each point of S1? So for each element here, you have a copy of R. Okay, so the way to think about this is you take a strip like this that you see here. Okay, and if you look at the blue line as a blue line here as the circle, right? Then you can see all these vertical lines, that's a copy of R as you go around, right? So if my finger is a copy of R, this moves smoothly as you go around each point of the circle, okay? And of course you know that there's a Mobius band where instead of tying the ends together like this, you can twist, put a twist in there, and then you get an interesting line bundle, the Mobius band, okay? So, well, what's one way to construct the Mobius band? I mean, I've showed you one quite physically, but actually the best way to approach this sort of problem is to use Galois theory. And that's what I want to show you right now. Okay, so what do I need to do? And I want to follow the type of setup that I have here again, okay? So it can be very, very similar to the type of things that I want to do here, okay? So the first thing is that I need something that's like the complex numbers. Okay, so in this case here, the object that's related to S1, okay, that plays the role of the complex numbers is the real line. Okay, so the real line is nice. Okay, so why is the real line nice? So it turns out that the real line is a contractible space, so all line bundles on it happen to be trivial. So this is just a fact from topology, and in general, the analog of this fact that, so what works for you here that makes the question easy over the complex numbers is the fundamental theorem of algebra, the fact that it's algebraically closed. In this case here, the reals is simply connected, so that's the analog of algebraic closure. Okay, so you have the reals. Okay, great. The next thing that you need to do is that you need to relate the reals to this S1 and also have some sort of a Galois group. So let me show you what's happening here, okay? So we're going to start with R, okay? And so that's like our C here. And whereas before you had this conjugation, we need some sort of group action here. So the group that I want to look at is just the subgroup Z. That's going to be my G. And it acts on R. Okay, well, it's a subgroup, so of course it acts just by the usual restriction of the regular action on R. Okay, so remember R is an additive group, it acts on itself, so you can restrict that action. So more precisely, if you have an integer Z that's inside your reals and it wants to act on this alpha, you just do n plus alpha. So n maps alpha to n plus alpha. Okay, so that's the action that you have, and now we can look at the following cover. Okay. This is an example of cover. It's going to be map pi from R to R mod Z. Okay, so this is just a quotient map that you see in algebra. Okay, so alpha goes to the coset alpha plus Z. Okay, so that's what you have here. Alpha goes to alpha plus Z. And the thing to note is that, of course, this R mod Z, if you think about this as topological spaces, here's a topological space that you have here, and this is a quotient topological space. This quotient topological space you can think of a couple of different ways as this coset, or also just the orbits of this R under this action of this group Z. Okay, they're both ways of doing it. And if you look at that topologically, you just get S1. Okay, if you don't see that, hopefully you can see that from this picture that I'm going to draw over here. Okay. So what's going to happen here, okay, is that now what I'm going to do is I'm going to draw this R. I'm just looking at it as a topological space. So it's going to be a line, but I'm going to wind it around like this. And the way I'll do it is as follows. Okay, so for each real number alpha, when you increase by 1, you'll get up to the point that's basically on the next rung up, the next rung of the spiral up, when you increase it by 1 like that. Okay, and what does this map R to R mod Z do? Well, it identifies alpha with alpha plus 1 plus alpha plus 2 and so forth. So basically you've got a map which kind of projects this down onto the circle like that. Okay, so that's one way to kind of see that R mod Z is actually homeomorphic to S1. Of course, you can do this lots of other ways, and another way that I guess you can do this is you can actually write this map more specifically just by using the exponential function, for example. You can do E goes to the exponential of 2 pi I alpha. Okay, so remember e to the 2 pi I n, okay, they're going to map to just the trivial to 1, okay? So that's what you can have there, okay? So that's the way you do it formally, okay? And so now the Galois group, so here we have the map here, so we've now related this R to this S1, and you have a group Z that acts on this, okay? So that's very much like the situation that you have here. You started with this R, which is like our S1. You have this thing kind of over it. The C is now this R, and you have a group acting on this, okay? So let's see how the group acts in this sort of picture here. So it acts by what's called deck transformations, okay? So this is the action, okay? But when you look at like this topologically, okay, it gives you a different sort of a feel for what's going on, okay? So let's see how 1 acts. 1 means you add by 1. So basically you move around this spiral until you spiral up 1 rung, okay? So alpha goes to alpha plus 1 here, alpha 1 plus 1 goes to alpha plus 2 here, and basically you sort of move up the screw 1 rung. So this is called a deck transformation. You kind of go from one deck to the next one up or down, and if you act by other integers, you can go up quite a few decks or down quite a few decks. Okay, so that's the first thing to sort of notice about this this action of Z on this R. The other thing to kind of note is that, remember, whereas before, for this conjugation, okay, it will act on C, but it kind of doesn't act on R. Okay, so that's the key point. It kind of doesn't act on R. And well, so what's going on here? So this Z acts on R, and if you look above and you look down, okay, you look down onto the circle, okay, and see what's happening with this action. So one will basically wind you up from one point to one point which is just one above. So when you look down on the circle, what is it doing? It's just rotating. Action of 1, it just rotates by 2 pi, which means it doesn't do anything. So this group, it kind of doesn't act, it acts trivially on this S1. It does act on S1, but trivially, just as it acts trivially, the conjugation acts trivially on R here. Okay, so that's the analogy that you see. Okay, so the Galois group of R over S1 turns out to be this Z, which is our G here. Okay, so now what do we want to do? Okay, so we're going to do the same sort of thing that we did over here, okay? So what we did was we took our easy answer, which was x minus alpha, okay, these linear things, and then we looked at orbits of them, okay, to construct modic real irreducible polynomials, okay? And we're going to do the same sort of trick here, okay? So we knew here they had to be very easy, the answer that you have over C, okay? And similarly, remember what I told you about line bundles over R. R is contractible, so they have to be trivial. Trivial here means it has to be of the form R cross R. Okay, so this is, we're going to start with a trivial line bundle on R cross R. But what we're going to do is we're going to let this group act in such a way to get interesting objects. Okay, so what's the action? Okay, so here we have N is an element of my group. Okay, that's an integer, and it's going to act on this alpha V. Okay, so this is going to be my copy of, this is a line bundle over R. There's my alpha in the R that's over. And remember, this is a line bundle, so that means that you have a copy of R. Okay, so this is inside R for each element alpha in this R. So it's a little bit confusing because there are two R's, okay? So this the first R is going to give me the thing over S1, and the second copy of R is the line of the line bundle. Okay, so what is this going to be? How is it going to be defined? Well, what you're going to do is you're going to act on, well, remember it acts on this R to give you this. So we'll just do the usual action there. And then what you do is that you want to look at the line above this point alpha. Okay, and you want to act on this line, but you want to act as a vector space. So actually, these line bundles, they're really, when you think of this R, the second R, it should be thought of as a vector space, okay, a one-dimensional vector space. So you think, well, how can the group Z act interestingly on a one-dimensional vector space? And really, the only sensible thing that you can do here is you have to multiply by a scalar. And so let's put in the scalar minus 1 to the n times v. Okay. Okay, so that's what you're going to do here. And then what do you see here? Okay, so what do you see here is you have an action. You can check that this is indeed an action of this group on R cross R. And so since you have an action, you can look at the orbit space of this. And I claim that this is precisely the Mobius band. Okay, and we've constructed this in this way, which uses the principles of Galois theory in a general setting, and so has a good hope of being generalized to lots of other situations. So let's see why that's true. Okay, so let's just see what's going on with this group action. Okay, so we're going to start with R. This is going to be the R here, which is this R here. And basically what we're going to do is we're going to let the group act on this. So when you act on it, it goes by deck transformations. You're just adding integers. So alpha gets identified with alpha plus 1, which gets identified with alpha plus 2, and that will give you the circle. Okay. And then you have those orange lines, which are the lines of the line bundle. Okay. So let's just pick something here. Let's pick a point alpha v. alpha, and here's V. Okay, if you let 1 act on it, you move over by 1, and then you multiply this minus by minus 1, so that's minus V. So in the orbit space, this point will get identified with this point. And then if you add 2, okay, you just multiply by minus 1 squared, so it's the same V, so you got identified with this one. So this gets identified with that. Okay, so let's see what more generally what happens. Like if you look at this orange line here, if you look at the orbits, what do these points get identified with? Well, basically you have to move over by 1, and then you do the negation. So you sort of take this line and you swap it to its negative like that. So you basically take this orange line and you glue it to this orange line, but not in the usual way to get to the trivial one, but rather in the same way that you do to get the Mobius band. And then you glue that back to the other one. Well, of course, in the end of the day, you might as well just look at the bit where you just glue this line to this line and forget the rest, and you'll get the same Mobius band. And that's how you can use Galois theory, okay, to understand the general construction behind the Mobius band. I hope you enjoyed this adventure in pure mathematics.